we are going to cool down a can of soda. Now, when you see this kind of information, we've got temperatures, we have the mass, we have to calculate the heat, and we're given the specific heat. This is what I think of initially. There's the relationship that puts all of that information together. Now, before we use it, let's parse information. The mass of the solution is given as 369 grams. The change in temperature. I'm not worried about first whether it's cooling down or warming up. So I'm just going to figure out the change. We're given this specific heat capacity. And when you work these problems, I strongly suggest you not work it with the specific heat like this because of the combination units. I suggest you carefully separate it out into a numerator and denominator, and that will help minimize mathematical mistakes. So this is the way I suggest it. There, I have my numerator, I have my denominator, all the numbers, all the units are in place. Let's move the information around so I've got some room to work here. Since we're given the specific heat capacity, I'm going to start with that. Now, before we keep going, I got to make sure that we get this in the right place as far as the units. If you go back and look at the very beginning of the problem, it does say calculate the heat transferred in kilojoules. Well, there's joules here. I'm not worried about the kilojoules yet, but joules. So when you're done, do you want the heat units in the numerator, like this? Or do you want the heat units in the denominator, like this? Are you going to multiply, or are you going to divide by the specific heat capacity? Well, you want it like this, because you want the heat units in the numerator. Now we multiply and divide, make our units work out. That 4.18 joules per gram degree Celsius is not a formula. You do not plug it into that. You multiply and divide, unit analysis, to get your units to work. I'll multiply by the mass first. Cancels my gram units. I'll multiply by the temperature change. Cancels temperature units. And then we've got the joule to kilojoule problem. So there's my conversion to go from joules to kilojoules. Now on those pieces, you don't have to do it in that order. I always think of this as a slide puzzle. I do suggest you start with the specific heat capacity, but as far as the rest of it, it doesn't matter. Be consistent, something you can repeat. And then for significant figures, 4.18, 369, 22.0 all have 3 significant figures. So our answer has 3 significant figures. You see, I didn't even use the mathematical formula. But if you want to use the mathematical formula, it's all there. Each piece is there. The benefit to not depending upon the mathematical formula, well, there's 2 actually. 1, you don't have a formula to forget. But 2, it makes it very easy to do a unit change from joules to kilojoules right within the problem. Now, as far as the sign, the problem didn't ask for the algebraic sign. Now, here's a representation of our can of soda. And if you designate the soda as the system, then heat is flowing out of it because it's cooling down. And so if you say the soda is the system, then you put a negative sign on it, exothermic. If instead you say the outside of it is the system, then heat is flowing into the system, and so you'd put a positive value on that. Your refrigerator works by manipulating the system and the surroundings. When you condense a gas, it gets really hot. When you expand it, it gets very cold. So if you think about how the refrigerator works, at first thought, it doesn't make any sense, because the inside of the refrigerator is cold, the outside of the refrigerator is warm. Heat doesn't flow from cold to warm. It flows from relatively hot to relatively cold. That's where the compression and the expansion of the refrigerant comes in. You expand the refrigerant so it's now colder than the inside of the refrigerator. You transfer heat from inside of the refrigerator to the refrigerant. And then when that refrigerant moves to the outside, you compress it. It gets really hot. It's now hotter than the outside air, and you blow air over it so you can transfer the heat from the refrigerant to the outside air, and then you keep going.